Okay, we were waiting for the microphone to show up. I guess Dr. Schechter took it. Do you guys know? I mean, somebody had to be watching him. No? Nobody cares. So Marmina's up there standing in line, probably. Okay, the last time we left off on a discussion of the course objectives, so let's quickly go through this and talk about them. We're going to talk about the porosity, permeability, petrophysics, geology aspects. I do not have a strong feeling for how you're going to incorporate this into your understanding later on. This is more or less treated as a separate module, as is the oil, gas, and water properties, but you will have problems to solve, both exercises and homework problems on porosity, permeability, as well as the estimate oil, gas, and water properties. Did you find it? No? Yeah, I could. I don't know why it's not here, though. I assume this is picking up the volume right now. Okay, so you're going to have at least a homework and probably a programming problem on oil, gas, and water properties. In Petty 310, did you create a module to calculate oil, gas, and water properties? No. So this is an exercise that should serve you well later on. Then we'll talk about pressure trends, and we have various types of data trends that we're going to have you plot. You did an exercise on Wednesday where you plotted, some of you plotted points, some of you plotted lines, some of you plotted I don't know what. But those particular kinds of exercises are very important. You're going to have to recall how to do things by hand. Bill Gates is both your best friend and the devil incarnate, because you're going to walk up to Microsoft Excel for the rest of your career and use it to plot things. For about 15 years, I did not do that, and for the last 3 or 4, I have. I'm as good as you are, or probably a lot better, but I still do not like the way Excel plots data. We use a proprietary software, my students and I do, that makes production quality graphics, so most of the things you're going to see from us are that, but you'll also have to know how to plot by hand. We'll probably have some plotting exercises by hand on the both exams, and you'll certainly have some exercises, not a homework problem, but an exercise on plotting by hand. We're also going to look at different kinds of models which create trends. We'll talk about that quite a bit. You're going to be able to derive the simple material balance relations. You're going to do this in Petty 323 as well, so this will be a good exercise. Actually, he may not make you derive it, but I will. Slightly compressible liquid is like, well, sort of like a Coca-Cola if there was no gas in contact with it, if it wasn't at the bubble point. It has a certain compressibility, a level of energy in it. And then we'll also look at gas and water. And then the material balance formulation for a dry gas reservoir with or without compressibility effects. We usually give a problem or two on that. Don, you got any strong feelings on that? This is sort of reinforcing what's going on in 323, but relevant to what we need in 324. Then we're going to derive the steady state flow equations for horizontal and linear and radial flow. How many of you had me for 311? So we've done some of that, right? You don't remember it? And that 70s movie that you probably don't remember, Let's Do It Again. We're going to do that again and again until you get it right. This time we're also going to include pseudopressure and pressure squared. Why are we going to do that? Because we need to understand the fundamental definitions of pseudopressure, and that comes from this derivation. We also need to realize that pressure squared is always wrong, unless you're in Turkmenistan where the pressure is less than 2,000 psi. Then we'll talk about pseudo-steady state. Steady state means non-time dependent. There is no time dependency. Pseudo-steady state means that there is a time dependency, but it acts like steady state when you look at a snapshot of it. So looking at a snapshot in time, it may look like steady state, but in fact it's time dependent. Then we'll talk about the skin factor. Everybody get it out of their system. It's not some movie that you see, on Cinemax or something. It's one of the usual petroleum engineering variables that came out, and somebody decided to say that it's like a skin on the inside of the wellbore, and so it got the name skin factor. The skin factor is fundamentally a trash can. Everything that we don't understand that is a non-ideality in a particular problem will go in the skin factor. We can derive relationships for the skin factor, but they are for highly idealized models which are not practical. So the way we'll use the skin factor is as a trash can. It will be a pressure drop which we cannot explain. Now, that doesn't mean that we don't understand what caused it or this or that. It just means that maybe we cannot quantify it. And some of you may be thinking, well, is it constant or is it variable? And that's the trick. As petroleum engineers got very lazy. Once they took and created a trash can for everything they didn't understand, then they said, well, let's make it time dependent. Now, we won't talk about that in this course, but the software packages out in the market allow you to have a time-dependent skin factor. Now, what does that mean to those of you who are thinking carefully about what I'm saying? If you don't understand what the problem is, and you start allowing that problem to vary as a function of time, that function that you're quantifying as deviation from non-ideality, maybe in your mind that's okay. But sooner or later, you're going to come up with something that you cannot explain, and you've been modeling it by using something that doesn't really mean anything physically. And what's going to happen is you're going to try to explain to your boss why you did this, and you're going to look like a moron. I've done it myself once or twice. The software allows you to believe that you can quantify non-ideality by changing the skin factor. Don't do that, or at least don't do it without, going to the church or the mosque or something and looking for divine guidance. It is a tough, tough problem. The skin factor will have an effect in our vernacular as a constant pressure drop. It may not in fact be constant, but that's how we're going to think about it. So when we're looking at a particular pressure trend, the intercept will be corrupted by, if that's what you want to think about it, by the skin factor. So let's talk about that for just a second, very quickly. Ready? Landon? Ready? Okay, so I'm going to take some magic paint, and I'm going to paint a skin on the inside of the wellbore. Can you imagine that skin will cause a positive pressure drop, that it will choke the well? If I keep putting paint, will it make the pressure drop larger between the formation of the wellbore? Yeah, that makes sense. So as an impediment to flow, the skin factor makes great sense. Now, what if I tell you you can paint with some magic paint that will actually make the pressure drop be negative? In other words, when the pressure gets to the wellbore, physically, it will go up. Well, that's impossible. But mathematically, the skin factor doesn't care whether it's positive or negative. So you can use the skin factor to represent damage in a very systematic and sort of mentally consistent way. But when you start thinking about using the skin factor for stimulation, you need to change your mind, because that is not the right reservoir model. The well is fractured, the well is acidized, there's something different about the wellbore configuration. The skin factor doesn't know that. It's just a number that you assign to that. What's going to happen to you if you deal with old engineers is you're going to learn techniques in this course to analyze dual porosity systems and vertically fractured wells. I doubt we'll get to horizontal wells because they're really woolly boogers. But when you're done with all your analysis, your boss is going to say, well, what's the skin factor? And if you say it's -6, his brain's not going to process that, or her brain's not going to process that. But then if you try to explain to them that the fracture half length is 453 feet, and that translates into a pseudo-radial flow skin factor of -6, they're going to go, hey, let's go to lunch. They're not. It's not going to make sense to them. So you're going to have to be the one that translates what's happening in the reservoir to managers who are still thinking in very simplistic terms. Then we get to the diffusivity equations, and I won't spend much time on that today, but that's going to be a tough one. We're going to all suffer together through that. Dilhan, any comment for that? Maalox and aspirin and alcohol. What else? And You know, honest to God, you're going to see this on the exam, so you better pay attention. Then let's pretend that we can all speak different languages. You know, I'm sorry for all you non-English speakers out there, but we won, you lost, so you have to speak English, right? Is that the way it works? I mean, how many of you have been in the airport in Xi'an, China, and you're the only white person? How many of you have been in an airplane in Kazakhstan and you're the only white person? How many of you have been in Port Harcourt and you're the only white person? You know, things are a little different then, right? But we all have some manner of communication at this stage, except for maybe them tribes in Papua New Guinea who'd rather eat you than look at you. We know how to communicate with each other to some degree, even if we don't speak exactly the same language. Now, is there a universal language? Right on key. Right on key. Other than love, is there a universal language? Sorry? Math. Oh, okay. Yeah, I'll buy that. But is there a universal language that mankind created for speaking and writing? What was it, Esperanto? Yeah, that was going to be a universal language, but it didn't fly because only pointy heads learned how to speak it, and then they talked to other pointy heads, and they were going to try to eliminate us from the food chain, but that didn't work out. So we got to fall back on something, and it's going to be love or math, apparently. Okay, so we've got dimensionless variables. What does dimensionless variables mean? It means that we take something that's in pressure drop or time or this or that, and we convert it to dimensionless pressure or dimensionless time or dimensionless wellbore storage coefficient or dimensionless rate. And you're hearing the word dimensionless every time and you're going, oh, only another 30 minutes. Why do we convert to dimensionless variables? Because that's a universal conversion. Once it's in dimensionless form, it's basically y is equal to a function of x, z, t, whatever you want to call it, and the problem is set up just like any other math problem. Of course, getting it into dimensionless form, you're going to have to swallow a bowling ball and then pass it out another, well, at any rate, we're being recorded, so I won't say. But once you're able to utilize the dimensionless variables, you can create solutions for virtually any problem. And then you can write the problem in a dimensionless form so you don't have to carry around the equation. It's sort of like having a universal money. Like the dollar used to be universal, you know? Oh, jeez. Okay, so then we're going to derive analysis and interpretation plots. These will be semi-log plots, log-log plots, Cartesian plots. Some of them may involve the pressure drop and the derivative. And we'll show you how to apply them for drawdown and buildups. And then what we're going to do is we're going to take those dimensionless solutions, which are real pretty, and we're going to take your data, which is real ugly. And in the good old days, they had two pieces of paper. One of them you could see through and the other one you couldn't. And you would lay your paper on top of, or you would lay your data on top of the type curve, and you'd move it around, and you would get a match. Can't turn it sideways, it has to be square. And, you know, we're going to do that again. That's the best way to do it. Now, computers, we don't have to do that anymore, because computers allow you to use the mouse, and you can, by moving the mouse, you have one coordinate system, and the computer can have another, so you can drag your data and move it around. You guys have probably done this with some types of packages. But we're going to do it the hard way in here. We're going to use paper type curves because I want your brain to get an understanding of what this looks like. I'm going to go to my grave, you know, wrapped in type curves because I think people need to know what the solution looks like so that their brain can make a picture of it. When you were a little boy and your mom said, you know, duck, and I don't mean like duck, quack, quack, chicken or that sort of thing. Did she show you a picture of that? No? You don't remember? Let's go to this. Oh, you never got it. When you were a little boy, do you have some cards that show the pictures of things? No. Anybody else, when they were little, had a picture of a duck and learned what the duck is and say quack, quack? Well, that's sort of what we're going to do with the type curve. We're going to show you one type curve, and you're going to say infinite acting radial flow, with or without wellbore storage, with or without external boundaries, and I can use that to estimate permeability, skin factor, sometimes fracture half length, wellbore storage coefficient, etc. Dilhan, you think we're blowing their brains out of their skulls? Good. That's what I wanted to do. Then we're also going to have to take these solutions and we're going to have to analyze cases for which they were not derived. We're going to use the liquid equations to derive everything. Why? Because the liquid equations are easy, but we have gas problems. So what's the easiest thing to do? The easiest thing to do is take the gas problem and make it think it's a liquid problem. It's to transform it. And that's actually pretty easy. Now, do you think you can get your head around that? So if we want our chicken to be like a duck, okay? We put some funny feet on it, put a big nose on it, and then we throw it in the water. And what happens? It drowns, okay? So sometimes this concept of using this conversion process doesn't work, but for all practical purposes in your career, it's probably going to be fine. Then we're going to design and implement a well test sequence. Our well outside should be back up and running by then, knock wood. We're going to analyze production data, and we're going to spend a lot more time on this than I will today, but we're going to utilize production data analysis exactly the same as we do pressure transient analysis, but now, instead of using a laser scalpel, we're going to use a chainsaw. Okay, so if I were to go to the hospital and say, I want to give you a nose job, and I don't want to spend $5,000, I'm going to spend $50, and the doctor comes in with a chainsaw, what are you going to do? Yeah. So I'm just pointing out that when you start doing production data analysis, you're doing surgery with a chainsaw. And this is not a bad thing. This is part of your job because production data is something that you're always going to have at your disposal. They're available by commercial records. They're available within your company, etc. Hopefully, when you're done in this course, you will be an advocate for the best possible production data. We'll also talk about how to analyze flow test and then to utilize well test production data, etc., to characterize reservoir properties. So now let me jump out of this and come over to this section. And we're going to try, maybe we will, maybe we won't, but we're going to try to start making a lecture series for each, or something we can utilize for a lecture each time. And in this particular case, this is just an introduction to pressure transient testing. We're going to talk about the objectives, we're going to talk about the data, we're going to talk about analysis and interpretation. And remember, at every stage, remember the assumptions. We're usually talking about a base of a liquid equation, slightly compressible, nice, well-behaved system, and then we're going to apply it to things that it doesn't really conform to, but we'll talk about that later on. Okay, so the first thing is to provide some orientation, the purpose, the philosophy, and the objectives of pressure transient testing. So if you were to explain this in one slide, and you were to say to yourself, I'm going to explain Petroleum Engineering 324, pressure transient part of the course, to my father or my mother, how would you do it? Well, you'd sit next to Zanero, and you'd read this off, and you'd say the objectives of pressure transient testing, number one, is to evaluate the reservoir pressure. Well, that's what the book says. Sometimes people use it to evaluate the initial reservoir pressure, but in reality, Johan, how many times have we seen people run a pressure transient test to evaluate average reservoir pressure? Zero. I mean, in modern times, nobody's going to shut in a well longer. Now, you might be Venezuela, and you might have been in Venezuela when the strike occurred, and they shut in all the production for 3 months, the entire country. And from that, you might have a build-up test that you may or may not be able to estimate the average reservoir pressure. But how often does that happen in life? Never. People are not going to shut in wells indefinitely to estimate average reservoir pressure. Now, if you're a low bid operator, I'm not applying compressed an injection well, see whether you're producing or injecting, the equations are the same. So you shut in an injector, and you keep monitoring the pressure. In that case, it is going to fall off to the average reservoir pressure. See, so that way it might work. If you're out in that kind of environment where you're looking at water flood data, and they decide, we don't want to produce this anymore for a while, price is low, shut everything off, then monitor your fields. You may get some data that you hadn't really thought about, but nobody's going to shut in production for years on end. You can evaluate the reservoir fluid. Schlumberger has tools now that they claim they can drop in the well and it'll perform a, amino acid level sampling of this, no corruption. They have an optical fluid analyzer, a sonic fluid analyzer, a nuclear fluid analyzer, but you've got to get the tool in the wellbore to do that. So you can use testing for that purpose. And I'm sure Baker Hughes and Weatherford and Halliburton also have these kind of tools. Now we're getting to where you want to be. We're going to estimate reservoir properties. We're going to estimate variability, which is K, skin factor, which is S, XF, which is fracture happening, lambda, and omega, which is signal porosity case, etc. That sounds pretty interesting. So if I take Cottle here and I stomp his foot really hard, I can determine his threshold for pain. I might even determine his skin factor, so to speak. If I poke him real hard in the eyeball with a pencil, I might determine his permeability. As an analogy. I'm trying to make sure you stay away from it. Okay? Now, I'm going to try to estimate all of these parameters using what? What kind of data? Pressure versus time. If I ask you to go get me a cup of coffee, and you walk up to the front door and get me a cup of coffee, you get that on the back, right? What happens if I ask you to walk over to Ethiopia and get me a cup of coffee? Am I asking too much? Yeah. So sometimes we ask too much of pressure data, especially legacy data. In your career, you're going to see some junky data. Hopefully it will protect you from it as much as we can in here. The greatest adversary in well test analysis is analyzing artifacts. What does that mean? Things that you think are one thing, but they're actually something completely different. Does this happen to professionals? Every day. Even people that look at well test data all the time, you can fool us just like first timers. Because the data have different signatures for different effects, but there are some that are almost identical. We can estimate fluid volume. Now, how many people are going to leave a gauge in a well with a high precision meter at the surface and measure that until you see depletion? Anybody? Sorry? Yes. Saudi Aramco puts the pressure gauge at the bottom of every well and the meter at the top of every well, every new well. There's been a pretty bit of old wells as well. And some other companies dealing with deep water offshore, North Sea, that kind of thing, they will as well. Now, here's the rub. Where's the data go? It's being spun onto some hard drive. Chances are nobody will ever look at it. I was down in Mexico one time and went into a little data room in San Maria Field outside of Hermosa. It's about 15 by 25 feet or something like that. And separate people in all the computers. And they were taking data continuously in the field. And I said, what do you do with the data? He goes, oh, I'll show you. And he pushed open a door that was the length of the room, sort of. And it was nothing but retractable hard drive with the data on each one. And I said, well, when Mexico City wants the data, and he stopped me and said, because they can come get it. So they never even saw it. Now, the input data for our analysis is going to be bottom hole pressure data. That means it's accurate to 1 part in 10,000 Is that a good thing? What's the old accuracy? Maybe 5 parts in 1,000. So you get 2 significant digits. I'm claiming you'll get 4 or 5 here, but you probably won't. Now, different companies, Halliburton claims they've got a gauge that's good to 1 in 100,000. Baker Hughes claims they've got a gauge that's coming out that's good at 500 degrees Fahrenheit and 35,000 psi full range scale. You know, I don't know, this is their job. They are supposed to come up with better and better tools because there's a need for this. I just want you to remember that not all of this data is going to be the quality that you think. And I have been fooled many times by a gauge that fails and it looks like it's still working. Beware of things that go on and go back off and then come back on. It happens. Surface flow rate data. This is another pressure fancy testing. This can be a real frustration. For production data analysis, you take what you can get. For fluid properties, we're going to need to have either a lab report or some sort of data set. And we need reservoir properties, thickness, porosity, wellbore radius, which is usually bed size, total compressibility. Did anybody here go to a seminar this week? Pressure level seminar? You know you're all invited, right? Did you like seminar? It was confusing, wasn't it? He was trying to tell us about the uncertainty and the 3 parameters that go into the reserve equation. What are those 3 parameters? H, V, and A. What are we getting out of this? We're getting a volume. We're getting a contacted volume in place. If porosity is wrong, doesn't really matter unless you try to convert that to an area. If thickness is wrong, doesn't really matter unless you try to convert that to something else. But porosity and thickness are important for how you're wanting to use that volume. I can tell how many molecules are in a reservoir by how the pressure behaves. I cannot tell how they're distributed in the reservoir. In order to do that, I have to know the dimensions of the reservoir. The results are we can get the productive capacity of the well, which is something that you want to know. That tells you whether the well is damaged or stimulated. You can always do both. You can damage a well, and you can stimulate a well. And you can spend a lot of money doing either one. Obviously, you don't want to damage a well, but you can. Productive capacity of the reservoir. This is what the true capability of the reservoir is supposed to be. And that's what we're trying to determine. The current average reservoir pressure, again, that's kind of a dream. Reservoir limits, that's a dream. We're not going to have a high-resolution extended flow test so that you can determine the reservoir volume. Every single textbook tells you to do this. And in practice, nobody ever can or will because it's not possible economically. Now, well interference effects, what does that mean? That means these are multi-well fields. And sooner or later, the pressure distribution from well A is going to interfere with well D and well E and well B and so forth. And when they do, we have to be able to quantify or at least recognize it. And then the last thing is the well and reservoir specific parameters. Dylan, have I left anything out? How are we doing on time? Since my watch died. Oh, came back on. We have 20 minutes. All right. This is a match of an unfractured well and a fractured well. This is like an ink blot test. Have you ever seen one of these before? Do you know what's what on here? This, hopefully doesn't screw up, is the raw pressure drop data there. This is the raw pressure drop data there. Okay? Those are the physical measurements that somebody acquired. They both look like hockey sticks, right? There's not much character. How do we get more character? How do we get more information out of data? Well, we cheat. And in our case, the way we cheated is we took the derivative of each. Marmina, these derivatives look pretty good, don't they? You know why? Because I'm real sneaky and I'm real careful about how I do this. I use my own algorithm. You know what I mean? And I delete points whenever they offend me. Do you think derivative algorithms are going to have a problem on the ends? Of course they are. Remember, the central difference is the best derivative, right? Forward, backwards. So you're going to have a problem at the endpoints. Whenever the software says, do you want to perform endpoint correction, what is it actually doing? Bill Hunt? It just replots the data without those points. That's kind of sneaky. Okay, what's the other function? Anybody? In this case, this is a contrived function. We called this the beta derivative function. We created this so that we could uniquely identify a flow regime. In this case, our nemesis is something called wellbore storage. Wellbore storage, sorry I can't draw a straight line, is a unit slope. It's 1 to 1. So if I take a molecule of fluid out of the wellbore, the pressure drops that linear relationship. Okay? So if I take the derivative and the pressure drop functions and I divide one by the other, I get a unit relationship. Okay? And then if I continue to plot that, the data trends down. Now this is a radial flow case, and there isn't a way really to distinguish anything with the beta derivative. The beta derivative helps us when we're dealing with non-radial flow cases like fractured wells and horizontal wells and sometimes dual porosity systems. So let's look at that one. Here's the raw data. Here's the derivative, and I'm marking this such that I can take those two functions. And then I take and I define a data function. Here it's unit, so that's wellbore storage. Here it changes. Here it's a half. Guillermo, what does a half derivative tell us? It is an infinite conductivity vertically fractured well. This is a signature. How many of you like snakes? Yeah? You know the difference between this snake and that snake? Yeah, you just chop their heads off. Right? Oh no, you're the one that likes to play with them. How many of you are going to sit there and count rings? Or say if the head's triangular? How many of you are going to drop a hoe on it or take off running? The same thing's true here. There is a distinct way of telling what the diagnostic is. And we're going to teach you how to do that. But you can see that characteristically, these look completely different. If the situation tells you, for example, that there's a horizontal derivative, that means you can calculate permeability. Okay? Now, I need you to distinguish something very quickly. The data are our measurements. The line is a model characteristic. Does everyone understand that? If there are no data, then we have no idea what the model is, right? So if I tell you that this particular model says that this is flat, but I don't have any data here, that's not unique. Same over here. The data stops here. The flat spot is over here. So both of these analyses are non-unique. Yes, please. Okay, that's a very good question. Nope, very good question. What it is that pressure drop is equal to a constant plus some constant times the logarithm of time, right? Take its derivative, what do we get? That goes away, and that's B over T, right? Multiplied by T, and that's B, right? B has permeability inside of it. So whenever you see a constant value of the derivative defined by data, when you're looking at a particular data set and that function becomes constant, and this model applies, then you know that you can calculate the permeability from them. In this case, it's 162.6, or actually in this case, it's 141.2 QB mu over KH would be that, is what B is equal to. But we'll go through all these derivations and discussions and so forth. But if you don't have any data that lies on the blue line, or if your data is not constant, then you cannot estimate the permeability uniquely. That's the point I'm trying to get at. So the first case I'm showing you, we think this is the right answer. But in fact, it could be here, or it could be, up here, and this is just an artifact. We don't know. But at least within some degree, we can estimate the permeability. It is a logarithmic scale, so you have to be careful that your brain doesn't say, well, it's not that much. It could be a factor of 2 or 3 pretty easily. And when we grade your exams, we're going to expect you to be right by process. The number can be wrong by, 25% would be okay, 50% I'd start worrying if you really know what you're doing, 100% maybe, you have no idea what you're doing. But diagnostically, what we're trying to get across is that you can see the behavior from this. Okay. Other questions or comments? Yes, sir. Unfortunately, this is an economic problem, not a technical one. That whoever your boss is wants you to run the shortest test possible. And if you tell them that, I'm going to put a memory gauge in the well for 3 days, and after 3 days, he expects that well to be back up to 100. If you put surface readout, then you can watch, and you can say, okay, I see the trend, I stop the test. But surface readout is 5 or 10 times more expensive than memory gauge. In this particular case, both of these are classic literature articles. One of them is from the definition of the pressure derivative. It's SB 12777 by Bourdain. The other one is SB 9975. It's leading voltage. And they're both perfect cases of how, at the time, people were looking at this well test and they were trying to make distinct sheet characteristics and all that sort of thing. And then we look at it now and we go, that's what's the log of the PEA. And we'll give you stuff like this on the exam. If you look at the exams that will be parked in the 08, 07 folders, they will be too short. Because we want you to give us your engineering judgment. Now, this is not the only plot that will apply. We'll also use semi-log and Cartesian plots, but we're going to capture some of them. We're still going to be sneaky and time to time. We're not going to give you the whole answer. Now, Bill, I think it's safe to say that we're probably okay for exam 1. We're not going to do anything sneaky there. But for exam 2, you'll probably see a case where maybe we didn't let it get all the way ready to flow. But as I was telling Clayton, you can still get an answer that's within 10%. We're not going to do something like truncate the data here. That's impossible. Now, you will see data like that. Now, a while back, I had a former student who went out and convinced his company to run a pressure transient test on a fractured well, and the permeability was 0.001. Should have never done that to start with, but it did. Instead of using optimal shut-in, used surface shut-in, took an 11-day pressure buildup test, and it was all wellbore restored. Because after 11 days, the wellbore is still not in equilibrium. That's crazy. But, it's going to happen. You're just going to have to tell them, I'm sorry, there's nothing you can do with this. Okay, let's see if this thing will do anything funny or let me go. Okay, these are some of the static data, and we'll talk about this some more. But fundamentally, you're going to have to be able to estimate fluid properties. You're going to have to be able to estimate reservoir properties. The single most important thing you can do as a reservoir engineer, I'm not talking about somebody who runs economics, I'm talking about a classic reservoir engineer, is have the well file on your desk or in your lab or open on your computer screen and be looking at what somebody's done to this well prior to your analysis, either pressure transient analysis or production analysis. It's absolutely critical that you look at the well file. I'm telling you, you will regret with extreme and excruciating pain if you do not look at the well completion history when you start looking at production and well test data. Now, here's another problem. In Texas, you've got 500,000 operating wells. And in Texas, you're allowed to allocate data. You're allowed to report by lease. And then people are back allocated by well. This is very common. It's also very common in certain countries where they split their production out. They're only looking at gross production. So you may only have a measurement a month that reflects reality. Just be very careful with allocated data. Now, the other thing is poor and incomplete pressure records. And like I said, the well completion issues, there's always going to be something that somebody did that they didn't put in the report. This is my favorite case in the universe. Everybody has their first love. This is not it. This is my second love. This particular case is an East Texas gas well. These are the gas rates on a daily basis. You can see the production is pretty good. It's a little bit noisy here due to some liquid loading, like that. And then this is a surface pressure profile converted to bottom hole. There's some jumps, especially where there were some zero rates. Now, I know you guys don't love this data set like I do, but you're gonna. Anybody want to tell me what this is? So we have daily rates and pressures on a tight gas well. Absolutely magnificent data. What's the green thing? The green thing is the genius behind a really good reservoir engineer. This guy wanted to compare production data analysis and pressure change analysis. He went to the reservoir engineering manager. Reservoir engineering manager said, "Do not shut in that well or you are fired." We walked down the hall to the production manager. He said, "I think that well has a problem. I want to shut it in." You got a test, just like that. The green is the measured bottom hole pressure from a properly executed pressure transient test for 11 days, something like 11,000 points. High resolution, high quality data. If you take the production data in red and the production pressures in blue and perform an analysis, and you take the pressures in green and perform an analysis, this analysis is for the entire life. This analysis is for that few hours or few days in the life where you're going to get the same reservoir properties. 3 options. Yes, no, maybe. What's the answer? Yes. Sorry? Right, but, oh, okay, I see what you're saying. The test has to be long enough to see the reservoir. Okay, but that's not what I'm talking about. I'm asking if the test is long enough, the production history is long enough, and we compare pound for pound. We take the data from the production history and we send it to the algorithm for production data analysis. We take the data for the pressure transient history and we send it to the pressure transient analysis. Are they going to give us the same result? Intuition says at best, maybe, probably no. But this is an unusual case. It is very low variability, 0.0055 millidarcies, which means that things happen slowly. And it turns out that the production data analysis for this case is actually as good, if not better, than the pressure transient analysis. And why is this important? We didn't shut the well in for the production data analysis. We used the history to achieve the same results. I know it's time to stop, so I'll show you the pressure transient test. These are the 11,000 pressure points. These are the derivatives of the 11,000 pressure points. How many of you have seen a pressure transient test before analyzed? Yeah? Okay. So tell me, did we do a good job with this? No. You don't like it because this isn't perfect, right? You know why it isn't perfect? Because we didn't take the analysis of this data. We took the analysis of the production data and we imposed it on this data. So this is a world-class example of taking good data, analyzing only the part that you wanted to, and then imposing that analysis on the other part, and bang, you get the same answer. Within a few, you can see the slight difference between the data here and here. But that's a pretty phenomenal accomplishment. Okay, we're going to hand out these books. Scott will grab a box.